Okay, so this slide is pretty much about what all we are going to be covering. We covered the summarization yesterday, and today we are on to filtering. These are the objectives and pretty much clear from what is written over there. In addition to the filtering design patterns that we discussed, in the end we'll also, as I said yesterday, we'll talk about some details. Okay, so what is a filtering pattern? Basically what you're trying to do in filtering, I mean it's quite apparent from the name itself. You are trying to take out the subset of the interest from a larger set of data, and that's what you want to work on. Maybe on doing some analytics further on that. So initially you want to get a subset of the data. The applicability of applying a filtering pattern is quite ubiquitous. You will see this in numerous places, and a few examples which I can give here is when you do a machine learning algorithm, for example, when you are trying to train a machine learning algorithm, a classifier or for example a clustering algorithm, generally if that algorithm doesn't run a very parallel architecture, the chances are if you give it a lot of data, those algorithms will slow down a lot. Your training is going to take much longer time. So what you want to do is you want to get a sample of the data. Rather than giving the full data to such machine learning algorithms, you want to get a sample of the data. So we'll see a pattern for this, and that's sampling. It's not exactly a pattern because the criteria of a simple random sampling uses for figuring out what is to be kept and what is to be discarded is very different, which you will see when we come to discussing that pattern. So in filtering patterns, we are going to be talking about 4 different kinds of patterns. So we'll talk about a basic filtering pattern. Then we'll look at the Bloom filters, top 10, and distinct pattern. And although all these are filtering patterns, so the way they are applied and the way they are used is different. So there are nuances to the way you implement this, and that's why it's important to understand each of these in a context of their own. Okay, so we start with the basic filtering pattern. So the example I gave you earlier, where you had used one of the MapReduce jobs as the pattern, that is an example of a basic filtering pattern. So basic filtering pattern, what it does is there is a test condition, and you apply the test condition on the records which are coming in, and then you filter in or filter out data based on the success or the failure of that condition test. That's what a basic filtering pattern is. And one of the examples of this could be, for example, if you have your weblog data and you want to do more analysis, traffic which is happening on your website between 10 and 11 a.m. So you would go ahead and filter all the records which belong to those 2 hours and do further analysis on it. This is the diagram for basic filtering pattern. It's very simple. So as you can see, in the filter mapper is a place where we are checking for the condition, and input split is processed by the mappers here, and based on the condition over here, the records are either filtered out or filtered in. So how the mappers, combiners, partitioner, and the reducers used in this pattern? As you have seen in the diagram, we had not required any combiner. There was no partitioner, and there was no reducer as well. but you could use a reducer, an identity reducer probably, but generally it's not required. Actually, if you probably use an identity reducer, in some sense it actually becomes like an inverted index pattern and filtering pattern applied together. There is some analogy here with respect to SQL and PIG, and as you can see, statements used both in SQL and PIG to get the same kind of behavior. And in SQL, it's actually the where clause which provides you that, and in PIG you have a filter keyword itself which is doing the job. So yeah, again, some of the use cases we have discussed some earlier. If you want to have a closer view of the data that you have, you filter out the subset that you want to have a look at. Removing low scoring data, this is another use case, and we'll see an example of this later in this class. Doing a distributed grep, so grep actually is a filtering command itself, but if you want to really do a distributed grep implementation, then you can do this on MapReduce. Data cleansing, again, you can look at it as a filtering pattern because you clean out the stuff which you don't really require. We'll look at simple random sampling in the slides later, and we'll talk about it there. And then we have tracking a thread of events. So you want to take some action based on certain events which are coming in. For example, you are reading from tweets and you want to take some action based on the kind of tweets you're receiving. So you could use a filtering pattern over there. Okay, so with that we come to the first example here, and that's the example for the basic filtering pattern, and this is called remove low scoring data. And the data which we are going to have a look at this purpose is posts.xml file. I have not sent you out these files yet because the size of these files is really huge. I'm trying to reduce them and reduce them in such a way that some of the connections between all these files is maintained somehow. And I guess in the next 24 hours I should be able to send out these files to you. But for this example, so just keep in mind they are just XML files with different in there. So there are row IDs and then there are different fields. And one of the fields in there is the comment count in posts.xml. So this is a count of the comments which have been made on a particular post on Stack Overflow. And now this is also an indicator of how popular that post has been, because you will find more comments on the posts where which are actually more popular. So how we implement this? So we will filter out the records that have comment count equal to 0. Okay, I'll show you the code for this first, and then I'll show you a demo. So here it is. Let's see. Let's look at the driver first. And don't worry about this error that you're seeing here. This is, I actually did the development on some other platform. I just copied this file over here, so you're seeing this for showing it to you. Okay, so we have a mapper and we set it here on this line, and the number of reduced tasks is set to 0. We don't need reducer, although we could have used one if we wanted to use an identity reducer. And I said that could have been something like a combination of inverted index and a filtering pattern. And as far as output is concerned, the values are, you don't need the keys in the output, so we are just doing an output of the values. Okay. Let's see the mapper. So it's a very simple code. So we just get the comment count, and based on the comment count, if it's 0, such things are actually removed. And we are just using a counter for that purpose, remove counter. And then we also write these values out from to the disk. That is a code for this. Let's move on to showing you a demo for this. Okay, so here is the remove low scoring data, the code that I just showed you, and we are running this. Okay, so as you can see at the bottom, this is the counter which you had, and it had removing 2,409 records from posts. That's if I know the number of lines correctly, probably that's almost 50% of the records are gone. So that shows only 50% of the posts are generally having more popularity. Okay, let me take, if you have any questions. Is this file in LMS? So are you talking about the file which I just showed you, posts.xml? Okay, Java file. So all these things in the next 24 hours is going to be in LMS. Okay, can you show some example with unstructured data? So the stuff which I showed you is actually unstructured data. I'll show you. So it's, in some sense it's unstructured, but in some sense it's definitely structured as well. It's semi-structured. I will show you a few things when you do some training with the Bloom filters. Okay, so yeah, so a little comment on that actually on the unstructured data. So even if the data that we have is unstructured, in some sense by using text analytics you will have to gather structured data out of that before you can go ahead and do more processing on this. So one of the ways of dealing with unstructured data is to do initial annotations on that unstructured data so that you get some count values on the annotations. So for example, I was talking about the place in a travel blog, for example, right? So by doing text analytics, you will end up putting annotations of place and the spots in that file, and then you can do further counting or a few other things which I just talked about on that data. Next one is simple random sampling, and I did tell you earlier that this is quite useful when you are trying to apply machine learning to your data. As I said, machine learning on huge sets of data is cumbersome because the learning itself, the training of the model itself slows down substantially. So you actually do a set of that big data, and you simple random sampling so that random sample that you have is actually a good representation of the actual data you have. And then you can use this simple random sampling to do your training on the classifiers. So we'll see an example of this. And simple random sampling is also a map only job. One thing to be kept in mind is when you are doing the sampling from this big data set, the chance and the probability of each of these being selected is exactly the same. So for example, if you are doing a selection from a record of 100 data set, a data set with 100 records, and you're trying to get a sample which is 10%, then the random sample is actually going to make sure that you have this data spread from all across. That's what random sample will make sure for. Okay, before we get to the demo, a few more things about simple random sampling. I think sometime back I told you that simple random sampling is not really filter kind of pattern because in simple random sampling, the test criteria that you're using is not actually based on the actual data set that you have. You are actually doing a test on the random number which is being generated, and I'll show you in the example. So in that sense, this is not really doing a filtering on any fields of the data itself, but it's doing a filtering based on the random number that's generating on its own. And I'll show you that, how it's done in the example that will follow. Again, our data set is posts.xml. And from this, we are trying to get a sample which is probably 0.5%. The example which I'm using here is getting 0.5% of that whole data. And then you can use that stuff for doing further processing, like training a machine learner. Here is a driver, and we're setting the mapper class, and we're not bothered by the key, so that's we're setting it to, we are using null writable for that purpose, and the value is written as written out. And again, we set the number of reduced tasks to 0, so it's a map only job. Let's see the setup function here before we get into the map. So here's the crux of the simple random sampling. So we have provided a filter percentage. So I want 0.5% of the records filtered out. So that's just if you come to the mapper, then here is a code for that. As I said, right, the test condition is not based on any records. What you're testing here is this is a random number which is generated, and if that random number happens to be less than the percentage that you're trying to get, then you write that value out. So here it is. So the mapper has got a key value pair. It does not do anything with that key value pair. What it's doing is it's generating a random number, and on that random number is checking whether this random number is within that percentage. If it is within that, just output that. That's the logic here. So how does it work? If it's a little bit confusing. So okay, so if you say me there are 100 records, and you say get me 10% of these records, what it's doing is, based on this random number, if the random number that you have is less than 10, it's outputting it. And remember, because we said the chance of each of these being picked up is the same. So 10% of the time you will have values which will be picked up, and that is which is below 10. Okay, so end up having that many records even without having a look at any of the values in the fields of the data. Okay, so we have so far seen the basic filtering pattern, and now we come to a special class of filters which is called the BloomFilter. And this is important because it's used in a lot of places when you're dealing with big data. And the very benefit of using BloomFilters is the amount of space a BloomFilter takes to store your data, to store a larger set of data, is much lesser than if you had not used a BloomFilter. So let me talk about its structure in a little bit more detail. So there is BloomFilter actually maintains set of set members. Okay, and anything which is part of this set will be filtered in, and anything which is not is going to be filtered out. And these set members are called the hot values. In the subsequent slide, I'm going to show you a full description of this, and it's a structure as well. On this slide, you just keep in mind that it's useful from the purpose of the fact that it actually takes much lesser space to store to do your tests on the data, and also there is a downside to it, and that downside is things which get passed out of these filters. They can either be true positives or true or false positives. False positives as well. What that actually means is true positives mean that things which pass out as true positives, it means that those values are the true values which should be in that filter. And false positives are the ones which mean that they have passed through this filter but actually should not have. But the amount of false positives which is generated using the BloomFilter is much lesser. So given the fact that in terms of the space reduction which happens because of using BloomFilters, that benefit pretty much outweighs these false positives, because once these values have passed through the BloomFilters, later on they are going to be used down the line in some other analytics, and over there again those tests would anyway be done. So false positives would be filtered out at that time. The benefit it's providing is you are not, so it's useful in cases where you have, where dealing with comparison of the data is much more costlier resource. So for example, if you have two machines, on one machine you're doing your data gathering from different places, and then there is another machine over the network where you do further analytics on that data, combining it with other tables which you have on the other server. If you don't use the BloomFilter, what will happen is all this data you will end up transferring over the network to that other machine, and it could be that only 10% of the data is for the operation on the other side. Okay, so you are incurring the cost of transferring this data over the network, and at the same time and if you are doing this, for example, if you are checking for that stuff in a database, you actually would end up reading a lot of blocks of data from the database, and ultimately those blocks would be discarded because whatever has come through they actually don't need to be used for analytics on that side. So to avoid transferring such data and use tests, which is more expensive to do on the other side, we use a BloomFilter on the first machine, and this BloomFilter would have extracted out only the useful information, mostly only the useful information, and transferred good ones to for operation on the other side. So from that perspective, BloomFilters become quite important. But you need to be sure when you're using filters, you need to be sure about what is the predetermined set of items which you will use as the hot values, and you will train that filter on. So there are two different steps when you're using a BloomFilter. The first step is you train your BloomFilter first on the hot values. Okay, when that filter is trained, that stuff is written out to HDFS, and then in subsequent jobs, which is about actually doing the Bloom filtering, use this BloomFilter object for the test. Now this test condition which we had seen in the basic filtering, the test condition was actually some kind of a if-else statement. That's not the case here. You are actually testing a set membership in BloomFilters. Here is a bit of a theory. So this is the internals of BloomFilter. So it contains of two things. You have a set of hash functions, and then you have a set of bits in an array. So it's a bit array that you have, and a hash function. Not a hash functions, a number of hash functions. Both these parameters, hash function and bit arrays in a BloomFilter, they are parameterized. So you can actually configure these. So you can define how many hash functions you require. Maybe I have shown in this diagram 5, you require only 2. And then in the bit arrays, the size probably is how many? Looks like 20 or something. So it depends on you how many you actually want to use. Okay, so now let's see. This slide is about adding to the BloomFilter, how the addition happens. So this is the slide for adding a BloomFilter. So we've used 3 different records for this training, so A, B, and C. What will happen is all the hash functions will be used on A, and A will be hashed by H1, H2, H3, H4, and H5, and then they will find a slot in this bit array. So as you can see, this bit was set to 1 because A was hashed to it, and this is A hashed by hash1 function. Similarly, you can see for A hashed by H2, you'll see A2 somewhere. So this is the place where A2 was hashed. A3 is here, A4 is here, A5 is here, and so on and so forth for other records that you have here. Okay. Now, as you can see, there can be collisions. In this place, as you see, both A and C were hashed by the hash function H2 into the same place. Not a problem. That's not a problem. We'll see why that is not a problem. See, if you see closely, there is for resolving the collision here, we have not maintained any list. Okay, so there are no buckets over here inside this. This is not a linked list. Generally, that's what happens in the hash tables, right? And that probably is done to avoid spilling much of data in this structure. Now that compromise is being adjusted by having multiple hash functions over here. Okay. So as you saw, so one question which could have arisen in your mind was why we are hashing with 5 hash functions. So one of the reasons for that is we are saving some space here, and to increase the accuracy of our hashing, we are trying to hash with 5 different functions over here. Let's see. So the previous slide showed you how we train a BloomFilter. So the previous in the previous slide we trained the BloomFilter with 3 different objects, A, B, and C, and that's how the bits were set. Now we are here on to our next slide where we are doing a query into the BloomFilter. As you can see, so record C was inserted. If you remember from the last slide, it was inserted. So when we query into this BloomFilter, again, this record is going to be hashed by each of these again. Okay, so C1 is hashed by H1. It comes over here. H2 over here. H3, H4, H5. Okay. Now, all these values that you're seeing, there's no collision. There's no collision in all these places. Okay, so there's no collision, and all these bits are actually set to 1. Okay, so that means the value which you have got is actually a true positive, because 5 different hash functions hashed it to some value, and there was no collision while retrieving it. So that means it's actually a true positive. They were definitely they were added to this hash table, and while recovering while you're using that BloomFilter, if you pass this using the condition that you have seen over here, it's going to be a true positive. Now we see another condition, that's about false positive, and here the D was not inserted earlier. So again, as you can see, H1 hashes it to some place, and it sees that okay, there is a 1 over here. H2 hashes it to the, it sees okay, there is a 1 here, even though D was not inserted because there was some other value inserted. So this value is 1. H3 is again hashing it to this place, H4 is hashing it to this place, H5 is hashing it to this place. So you see all the bits here have a collision. Okay, because all the bits here is a collision because D was not inserted, so these values are 1 not because of D, because of something else. So that means there definitely is a collision here. But just because watching in this bit array, we find those spots to be 1, the BloomFilter will assume that this record was actually a part of this set. Okay, and that's why this will pass the filter, although this is actually a false positive. Okay, now look at the case of something which is not passed, and that will be I don't have a slide for that here, but I'll just explain it. So it could be E over here, and E for H1 there is a 1 value, H2 there is a 1 value, H3 there is a 1 value. When we come to H4, you see there is a 0 here. The moment we see a 0, that means this is not part of, this is not going to pass the BloomFilter, so that's going to be discarded. So in short, that's the theory of BloomFilters, and you can configure these things based on your requirements, based on the kind of problem you're trying to solve. You can change these things. In the code which I will display to you, I have hard-coded these values, but there are methods to actually calculate them based on other parameters. And I'm not sure if I have given those formulas somewhere in this slide later on. Maybe I have, if I remember correctly. Then you can use those formulas and then derive the hash functions, the number of hash functions, and the size of the bit array before you train a. And BloomFilter object is something which is provided by your Hadoop framework. So this is the name of the BloomFilter object, and these are the fields in that. At least there probably are more fields in there, but these are the important ones. So there's a bit set that you just saw, bit array. This is the constructor. This is the add function using which you train the BloomFilter, and this is membership test. This is the actual operation of BloomFilter. OR key. So this is an OR operation. You can actually OR 2 different BloomFilter objects. And you will see examples of this in the slides later on, in the example that I use. Okay, so now we come to the structure of the Bloom filtering pattern. And we have seen the training part in the earlier diagram. And the two stages, this first step is the training, the second stage is using the filter itself. Although in the first step, what is shown in the diagram here is just using probably a single mapper and outputting the files, but we use multiple mappers as well for doing this task. Probably the diagram does not show it. It probably is using multiple mappers, but the diagram doesn't explicitly show that. And then you have the test part here, in which we load the filter from the distributed cache. So the filter was generated in the first stage over here. It was stored on the HDFS, and we load that into the mapper using a distributed cache. And then the BloomFilter test is done on that filter. And then we have the output file and the discarded set. I guess we have talked about this slide already. Yeah, one thing which I think I missed is, so you have trained the filter, and filter does not need to be retrained too frequently. But if your data as far as the set membership is concerned tends to change, then every time it changes you will have to train the filter again. Otherwise you will end up missing values, which probably should have been filtered in. So as far as looking for resemblance to BloomFilter is concerned in PIG and SQL, in SQL it's not there. As far as PIG is concerned, you can have it via user-defined functions. I guess natively still PIG does not implement it. Or if somebody is working in PIG and they have an idea, probably they can share thoughts on that. But my knowledge, as far as my knowledge goes, presently PIG doesn't support it native. So one of the use cases we talked about, and a couple of use cases we talked about, whenever you're trying to do checks with inside a database, and as I said, loading a lot of records which you ultimately won't be, that's a costly operation to do. And so Bloom filtering is helpful over there. And then also the case where we talked about transferring things over the network, and using a Bloom filter before we do that is useful. And actually Bloom filter is very important. Is getting a lot of attention because of its applicability in big data. It has existed for quite some time, but then because of the big data today, its usefulness is being observed. The very reason is the amount of time and the amount of space it takes to store Bloom filters once it's trained. And we can also do reduce site joins with Bloom filters. And we will see, and when we come to the join patterns, how we use Bloom filters for that purpose. Okay, so now we come to looking at some of the examples for Bloom filter. And we'll do both the things. We'll train and then we'll test. As far as the training goes, so let me explain this here. Okay, a sentence over here is a little confusing. I'm going to be using posts.xml both for the test and the training part. What I will do in the training part is I will look at the tags data in the post.xml posts, and then train the filter, and then I have got a list of tags, which is distributed using a distributed cache, and it's not a big list. It's probably a list of around 20 tags, and then I train the BloomFilter using the row in .xml if that row happens to have the tag. Okay, so based on the information present in tag names file, I train the BloomFilter based on information coming out of the body of posts.xml, and then later on when I do the tests, I actually filtered out only those records which had been trained on in the first instance. Let me explain this a little bit more with showing you the data set. Yeah, so here is a snapshot of posts.xml file, and as you can see in this row here, there are tags. Okay, and there's a JavaScript tag over here. Okay, these are the kind of tags we're going to have a look at to decide whether we need to train the filter on this post ID or not. These are tags which we're going to use, and this we'll distribute using a distributed cache. And we compare with each of these tags when we read these posts, and only those posts which confirm to this is going to be used for training the filter. Now let me show you the code for this. Here we have hard-coded the size of the bit array and the number of hash functions. This is the mapper class. We have a reducer, but we are going to use only one reducer. What this trainer does is each of the mappers will emit a BloomFilter after they have trained it on the data, and then all these BloomFilters will aggregate on one reducer, and reducer will do an ORing of these BloomFilter objects to come up with a single BloomFilter object which is written out to HDFS. As this key and the value do explain that, so I'm not bothered too much about the key here. It's null, and then you have the BloomFilter as a value from each mapper. And here we are reading things from the cache file, adding the cache file over here, not reading, sorry. And then we come to the mapper. So in the mapper, we have the setup method first, where we read the tags, and then we set from the configuration, we set these bit array and the number of hash functions, and then we create a BloomFilter object here. Okay, using the number of bits, number of hashes, and this is murmur hash is one variety of hash function. There are multiple ones, but this is one which is quite frequently. And then we come to the actual mapper. So we get the tags from post.xml, we get the ID of the post, and then we do some checking here. That's to do with whether it's contained in that or not, and then it's added to the filter. Okay, we don't write out the filter over here. We do this in the cleanup object. So this mapper is writing out this filter over here. Let's come to the reduce method. Reduce also, again, it reads the same values. It's bits in the hashes. And if I remember correctly, they have to be of, yes, they have to be of same size. And again, they are creating a filter using the same values like we had done in the mapper. And then because the key was null writable, so all these things are coming to the single reducer that we have. And then we are doing ORing of the filters over here. Okay, so we OR each filter one after the other to come up with a single filter which is a combination of all these, and then we write it out to the system at this place. And then we'll see in the test when we show you the code for the BloomFilter test. There we'll read from this object and then do the tests. Okay, so let me just show you the demo for this now. Okay, so the BloomFilter is written now to HDFS. If you have a look at it, probably it's because it's a binary content over there, you won't be able to see anything. Just to confirm on that. Oh, so sorry, it's actually not being written over here, it's being written somewhere else. Yeah, so you can't make anything out of that, but yeah, that's how the stuff was written out. And we'll see when we come to the test how many records actually pass. Yeah, so questions? Okay, if no questions, we move forward. Okay, so I guess I need to show you the training part because we have these two things being done together. So here is the code for testing now. So coming back to the driver code, again, number of reducers here is set to 0 because like the basic filtering, ultimately when you're doing the test, you don't require the reducers. So map only job. And here is a place where we are reading we're adding the filter object to the cache file. And let's see the mapper. So we are maintaining a counter here, selected counter, and we read, so this is actually a setup method, and we are reading from the filter object which we had created into this filter object. And then let's see what we do in the map. We actually do a membership test. So for a post ID, we want to check whether it's a member of this filter or not. So the membership test is done here. One thing to keep in mind is you have to convert these things bytes before you do the membership tests on them. Actually, while adding also, I'm not sure if I told you about it, you have to convert the keys into the bytes. So yeah, so if this passes, then we write it out. The post ID, we write that stuff out, and then we increment the counter as well. Let's see the code for this. Okay. Fine. So as you can say, 5,000 records were selected, and the record IDs have been written in the output file. We'll do a quick check on the question. Do you have any questions? Okay. Am I clear enough in terms of explaining these concepts? If you have any doubts, do ask. Okay, so let's come to top 10. So the next filtering pattern that we have in this list is the top 10, and it's to compare this with how you will do a top 10 when you are dealing with a much smaller size of the data. So in those scenarios, probably you'll go ahead and sort the data first, and then you'll take the top 10 out. But sorting being a very expensive operation, if you're doing it on large scale and if you're doing it on MapReduce, if you are in situations where sorting can be avoided, do try to do that. And we'll see one of the implementations here, which is of top 10, which will help do that, figuring out the top 10 records without doing any sorting. One thing you should keep in mind, and that's really important, is how many records you're actually trying to take out as a top. Okay, so if you are the numbers that you're trying to take out is much closer to your whole data, even 50% of your data, then probably it makes sense to go ahead and do the sorting itself. And I'll tell you why that is important. If you see the structure over here, so each of these mappers are going to emit the local top 10s. Okay. So if you're trying to find maybe the top 50% of the total data, then each of these will end up emitting in this pattern the same size of the data. Okay, 50% of whatever they received, top 50% of whatever they received as input split, and all these. So you, in some sense, you're not gaining anything, gaining much by using top 10 here, because the network traffic hasn't reduced, for one, and number two, the reducer also, when it's combining all this data together, it's going to maintain a sort of a list over here, and the size of that list is going to be much larger. So if the size of the 10 that you're seeing over here is much larger, you are probably better off just doing the sorting. But and this is a scenario in most of the looking for really top 10 best places to visit. On your dashboards, you want to see which are the top most important task items to be done. So if you want to see such data, then this kind of a structure and pattern is quite useful. And we don't use any combiner and the partitioner over here. And the mapper does most of the job, and use side there is a single reducer which combines the output from the mapper. There's not much of a use of using a combiner, because whatever data has to be transferred definitely has to go to the other side. There's no need of doing a combining here. And probably you missed saying about the partitioner. That also is not required, because the size of the stuff which is being emitted by each of these mappers is the same, and in the end probably the partitioner will end up doing a uniform distribution on its own. So how does it look like in PIG? So PIG behind the scenes will also be doing a sorting. So they probably don't do the top 10. So figuring out top 10 using order, by, and limit in PIG is not going to be very effective, and it's probably has issues in terms of the performance. Similarly, SQL is, of course, you will use these functions order by and decreasing limit. But then again, if you're dealing in SQL, probably you're dealing with much larger, much smaller set of data. So when comparing with pig, remember that although the statements over here look only a couple of lines, but internally it's incurring quite some cost. So the top 10 use cases, so we talked about a few, and on this slide we see a few more. So you have the outlier analysis. In some sense, top 10 is itself an outlier. Selecting interesting data for further BI systems which cannot handle big data sets. Maybe one of the use cases, yes. And publishing interesting dashboards we already talked about. Okay, so that brings us to the problem example that we have on top 10. And for this, we are going to have a look at the user. And for the users in this file, we are going to have a look at a field which is called views. And views give an idea as to how popular this user's posts are, because that views count is actually a count of how many times people have had a look at your posts or answers on Stack Overflow. So this data about having a look at 20 users gives an indication as to who are the most popular ones on Stack Overflow. We must take care of using only one reducer. Because if you don't do that, then what will happen is you'll have multiple part files, and each of these will have your top 10s or top 20s, and then they are sort of locally top 20 or top 10 in themselves. They are not globally top 10. Okay, let me show you the users.xml file first. Yeah, so these are the rows we have for each user, and as you can see for this row ID there is a views field, and each of these has views. So from all this, we are trying to figure out who are the top 20 users with most number of views. Let's go to the program. So in the driver code, we are setting the mapper class, the reducer class, and then we are setting the reducers to 1, and that's important to do. And then let's look at the mapper. Okay, so in the mapper we use this tree map, and the logic that we're using is we keep on appending, as we see the records, we keep on appending those records in this tree map, and the moment I go beyond 10, then I remove the user who has the least number of views, and just by using this data structure, which is top tree map, we can do this because tree map is going to keep things in a sorted order already. So what we do is we keep on adding over here. When the size goes beyond 10, at that moment we go ahead and remove the first key from that map. So this keeps on happening on the whole input split, and then in the cleanup we write all those values out. All those top 10 values is written out with the key as being null writable, and the value is the actual value. Come to the reducer. Code is similar. There also you see a tree map, and similar logic is followed over here as well. All the top 10s are routed to a single reducer, so you have all the values over here. And again, the same logic. If it goes 10, remove the first key. So what will happen in the end? You will have the top 10 users, and then we go ahead and write these values out. Let's run this code. Let's move to the last pattern for today, and this is distinct, and quite a useful pattern because for example, if you look at the CRM data, for example, right, marketing has this data, and they keep this data about the customers. There are a lot of duplicates in there, and actually there are products out in the market which are responsible for removing these duplicates. Distinct pattern is something which comes in use in such cases. If you have duplicates in your data, if you apply the distinct pattern on this, it will give you distinct records after removing all the duplicates. So this is a deduplication of the records. And this problem probably gets more magnified with the social media data, which is even less cleaner than more structured data which is present already in the CRMs. Doing that distinct is quite a useful pattern in those scenarios. Also, it's a very important pattern when you are, for example, doing machine learning. So if you have duplicate data and you're training a machine learner, probably a clustering algorithm in machine learning. The problem is if you have too much of duplicate data, you might end up having clusters around those duplicates, and the ultimate result might seem like you have a cluster where there are too many things in a cluster, and probably it's an important cluster, but what actually is happening is there are too many duplicates, so the values are clustering around some region. For doing high fidelity analytics, you definitely need to do deduplication. Here is the structure for the distinct. So so what you're outputting is the key is the distinct field from all these mappers. After the shuffle and sort, you have two reducers, and they get lined up like this, and then reducer's job to actually do the deduplication. And in the slide I haven't shown you the combiner, but combiner actually can be used here because if you look at this data, what we have transferred to the other side is duplicate data. So 2 is duplicated, 5 is duplicated, and ultimately reducer is working on this. We could have used a combiner over here and transferred maybe 1 and 2 from this mapper, 2 and 5 from this mapper, and 3 and 4 from this mapper. So that would have been a reduction in the network traffic. So it's useful. Combiner is useful if you feel that you have too many duplicates in your data, then using combiner is useful. But if you're sure that the number of duplicates in your data is not too much, but still there are duplicates, in such a scenario, probably using combiner would not have too much of benefit. There's some things written about performance on this slide. So how many reducers to use is slightly tricky in judging in most of the cases, but there are some heuristic rules which people tend to use. So one of those heuristic is to look at the block size, minimum block size and the maximum block size. So generally the minimum should be 64 MB and the maximum should not be more than a few hundred MBs. And this data you will get when you run your MapReduce job. These things are put. So by having a look at some of these, you can tune the number of reducers which you need to have. Generally, let's say that for the reducers to run half the time, double the number of reducers. So the distinct use cases, there is not much of a surprise on this slide. We have already discussed these. The last one, which is protecting from an inner join explosion, that's important. Because if you have duplicates on your duty and you're doing a inner join, there is going to be the results that will actually explode, and that actually can be in terms of some orders of magnitude. For example, if you have two tables and one table has got 10 records, the other also has 10 records, and these are without any duplicates. And then in these tables, so if you increase the records to 20 in each of these, and then those other 10s are actually duplicates of the earlier ones. And then when you try to do an inner join, the number of records which you will have as the results actually goes to 400. So from a size which initially was 100, it actually ended up going to 400. So the explosion in the number of records can actually be in terms of orders of magnitude. So be careful about doing inner joins with duplicates, and that's why this pattern also becomes useful. Okay, so we come to the example for this pattern, and for this we're going to have a look at the badges.xml file, and there are two fields of interest here for us: user ID and name. And the problem we'll try to solve is find the distinct set of badge names. Okay, so in badges.xml, I'll show you that file, and there are names for the badges, and because there are multiple records in there, there are definitely duplicates in there. So we want to figure out from these badges which are the distinct set of badges, and then we can use, for example, if I link it to something which we had talked earlier, we could link those set of badges, distinct badges, to train our BloomFilter, or even better, we could actually, if the number of badges is still huge after even doing the distinct, then you could on maybe the top 10. Whenever you look at these patterns, also try to look at how it's interlinking with some of the other patterns that we already viewed. That way you will be putting up a framework in your mind to connect all these patterns when you are up with slightly complex problems to solve. So let me show you the badges.xml first. So here is how this file looks like, and this name here is the badge name, and as you can see there are many in there and there are duplicates. What we're trying to do is remove these duplicates and have only distinct values. Okay, so let me do a setup. Okay, first let's see the program for this. So as you see in the driver, we have a mapper, we've used a combiner as well, And as far as writing the value is concerned, that is made null writable. That's not important. So we only deal with the keys here. And the mapper is simple. We just whatever we get, we set that badge name as a key, and the value is just null writable. And let's see the reducer. It doesn't do much. It's just writes to the context. Okay, so just a sec here. Yeah, so the trick here is we are not bothered about the value. What we are outputting is only the badge name, and so based on the badge name, these things will be grouped on the reducer side, and we write the key. We don't bother about the value. So ultimately, we'll have the distinct values written. Okay, I guess you understand this. So what we have is on the reducer side, we are grouping on the badge names, and then the values for a lot of values from the input split is actually are null writables, and we are just going to ignore that. So we just write the key. That's it. Fine, let's see the output. So here it is. So these are the badges, and as you can see, all these are distance, no duplicates left there, and the whole algorithm on this MapReduce design pattern was so simple.